Bayesian neural networks. Let's see. Let's first recap the structure of a basic neural network. A neural network has some features here in the input layer, and then there are some hidden layers, and then there is an output unit. Nodes in one of the layers is connected to a node in the next layer through typically weights. And if you see a simple instance of a neural network here, which is a logistic regression model where there are no hidden layers, in fact, just the input layer and one output, we see there are 3 features and 3 inputs here corresponding to them, and there are 3 weights. Each weight is connecting the corresponding input to the node in the next level, which is the output. So what does learning a neural network model mean? Typically, learning the neural network model means finding the values of these weights that connect nodes in different layers. And once we know these weights, we can actually compute the output from the network by doing a forward propagation step. This is all just a recap. Now, how does the Bayesian neural network differ from the traditional multi-layer perceptron that we have just seen? In a Bayesian neural network, instead of just thinking of weights that are connecting a neuron in one layer to that in another layer, we actually try to learn distributions over these weights. And as you can see here, this is, if you look at a deeper network here, you can have one of the layers as a Bayesian layer, where instead of just having weights, you can actually try to learn a distribution over weights connecting these 2 layers here. Now, what does that really mean, and how does it actually help? So what is Bayesian modeling? Just to recap once again. So Bayesian modeling enables us to handle uncertainty by learning a distribution instead of learning a single value for unknowns in our model. So in this case, instead of learning a single value for the weight through gradient descent, we want to learn a distribution over these weights. And what's the advantage of that? Once we have a distribution, we can quantify the uncertainty of our model. So if the distribution is very spread is very wide, then we know that we are less certain. If the distribution is peaked, like what you see here, then we are probably more certain. And as you see more and more data, your distribution would probably become more and more peaked, and you would be more and more confident of the prediction. The way Bayesian model typically works, once again, just to recap, is we start with a prior belief, or we start with some distribution that we think might be the right one, and then we look at the actual data and modify the distribution until we get something called the posterior, right? So now coming back to our Bayesian networks, neural networks, what we want to do is learn a distribution over these weights. So we start typically with an assumption for the distribution over these weights. It could be like a normal distribution, for instance. So here the notation is weight connecting layer node K of layer L to node J of layer L plus 1, right? And I could say it's a normal distribution with some assumed mean and variance. And the posterior is nothing but, okay, once I see data, how do I modify this distribution? Maybe it's another normal distribution but with different parameters. How do I find this new distribution that makes more sense as I see more data? So I have one distribution for each of the weights in the network now. So we know that typically to find the weights we use gradient descent, or we use like other optimization algorithms which are like variance. What do we do to find these distributions now? It's slightly different. We need to do some kind of approximate inference. The techniques that are used to find the weights are slightly different from the techniques that are used to find distributions over weights. The 2 popular techniques for approximate inference are variational inference, which involves approximating the distribution that we want to find with something mathematically simpler usually, which is more tractable, and then we find the best distribution of this form or the closest distribution of this form to the actual distribution we want to find. Now, how we do this is another story. We won't go deep into this now. And the other technique is MCMC, Markov Chain Monte Carlo, which is sampling based, where what we are saying is, because it's hard for us to actually evaluate this posterior distribution directly, we are going to still find a way to draw samples from it. Then the distribution itself can be represented through these samples that we drew out of it. Now, how do you predict with a Bayesian neural network? This process is slightly different as well. In a regular neural network, what you do is you give the inputs to the network, do a forward pass, and what comes is the output. For example, if you have sigmoid with cross entropy loss as the last layer, then you would end up with some kind of a probability as the output. Now, what would you do in the case of a Bayesian neural network? You don't have the actual weights now, but you have found distributions over these weights in the neural network. Now, from that, how do you compute the output? So what you actually do is you need to draw samples from the predictive distribution as follows. So you have all these distributions over weights. So you can draw a sample of a set of weights, which will give you one instance of or a sample of a neural network. You can actually draw multiple neural network samples, pass your input through each of them, and you get a different outcome from each of them. Now you can take a mean of these sample outcomes that you got to get, or you can do something else from this. You have a distribution over the outcome that you are expecting now, and you can take the mean to make a prediction. But not just that, because you have a distribution over the prediction, you can actually look at the variance to get an estimate of how confident we are about this prediction. And once again, the code for Bayesian neural networks is available. You have many examples of Bayesian neural networks being used, both for TensorFlow and for PyTorch. You can go and look up in the documentation. Now, what are the pros and cons of using a Bayesian neural network? Is it worth using one? So the pros are that it enables us to capture uncertainty over predictions. We have already seen that. We can know when our model is confident and when it is not, because we get a distribution over the predictions from which we can see how the variance is. The other aspect is that it's great if we know a good prior. For example, suppose you have a feature like gender, and unintendedly your network learns a very high weightage for the gender in some kind of a model where you don't necessarily want it to. You know that gender does not actually play a big role in this particular modeling problem. So you can actually give a suitable prior for that weight and control it. But finding priors is often very hard, and finding the right prior and an interpretable use case is great, but very often it's very hard to find a good prior. So the cons of Bayesian neural networks are that very often meaningful priors are hard to find. And the other con is the computational cost itself. So the cost of training a Bayesian neural network could be higher because you are actually doing this approximate inference, and often these techniques take computationally more time to learn, especially if you have a lot of Bayesian layers. But if it's a simple network with just a few layers and just a few nodes, it is often possible to come up with an efficient solution. At least with this level of sophistication we have with hardware right now, it is definitely possible. And it's not that hard actually. So for small networks, it works pretty well. For bigger networks, it could be a problem. And the other aspect is the cost of prediction is also higher, because instead of just doing one forward pass that we typically do in a multi-layer perceptron, we are actually sampling multiple copies of the network when we sample, a set of weights. And then we are taking an average. So this adds to the cost. And if you have an application where the prediction time is important, this could be an issue. So these are the pros and cons. Now to summarize, we looked at what Bayesian neural networks are. We looked at how to predict with a Bayesian neural network. We looked at what it means to find these distributions in Bayesian neural networks through inference. And we also looked at the pros and cons of using Bayesian neural networks. And finally, we saw that there are code examples available both on TensorFlow and PyTorch if you want to use Bayesian neural networks. Thank you.